Okay, so this is the first mini lecture in stellar structure and evolution. We talked about how a gas cloud collapses under the force of gravity to become a protostar. But what is it that makes it a star? Well, stars shine. That's pretty obvious. And they shine because they produce their own energy. Now, gravitational energy can make a protostar shine, mostly in the infrared part of the spectrum. But really what defines a star is when you have nuclear fusion, nuclear energy, the type of nuclear energy called fusion occurring in its core. You need a star of at least around 10% of the sun's mass for that to occur. So the lowest mass stars that are not failed stars are about 1/10 the mass of the sun. You might go down to about 9% the mass of the sun, but that's about it. Anything lower than that we call a brown dwarf because they don't really shine by nuclear fusion, even though they do give off some light. So, how does nuclear fusion work then? What makes stars go? Turns out that stars are so hot inside, there aren't really atoms inside stars. In other words, we think of an atom as a nucleus of positively charged and neutral particles surrounded by a cloud of free electrons that are bound to the nucleus. Well, inside stars, it's so hot that for the most part, all atoms are ionized. In other words, the electrons are not bound together in their electron clouds around the nuclei. They are ripped off because of the tremendous heat, and you have electrons flying around all by themselves, and the nuclei flying around all by themselves. Now, for the most part, about 98% of the atoms, probably a little more than 98% of the atoms inside a star are hydrogen and helium. About 90% are hydrogen, maybe another 9% are helium, and maybe another 1% are various other heavier elements. But for the most part, we can just think of it as almost entirely hydrogen and helium around a normal main sequence star that is just starting out in its life. The electrons have been ripped off and are flying around all by themselves. The positively charged nuclei are flying around all by themselves. Electrons don't like to be together. They will push apart because they are all negatively charged. And nuclei don't like to be together. If they approach each other too closely, they will generally push apart because of their mutual repulsion. Okay. Now, you can think of it almost like a natural collision avoidance mechanism. So if two protons, for example, two nuclei of hydrogen, are on a collision course inside the sun, for the most part, what will happen is they'll get very, very close, and then they will push apart and avoid each other because of the electrical force. The electrical force gets strong enough when they are really close to push them apart and avoid the collision, unless they are going too fast. How do you make them go fast enough so that they collide? Well, you turn up the temperature. Where in the star does the temperature get turned up so high that the nuclei can collide? In the core, because that's where it's hottest. We'll explain that in a couple of lectures. So nuclei can overcome this electrical repulsion because they are moving fast due to high temperatures in the core, okay, but only in the core. And the outside of the core is like the innermost 1/4 of the star's interior. Anything beyond that is called the star's envelope, and the envelope is not hot enough for protons and the nuclei to slam into each other fast enough to collide. So you might say, well, so what? So they collide, big deal. Well, when they collide, something very special happens. The nuclei have another force besides the electrical force that makes like charges repel. Okay, all nuclei are positively charged, and so when they get close together, they naturally repel each other with this electrical repulsion. However, there is a stronger force than the electrical repulsion. It doesn't take effect until the nuclei are virtually touching. when they are virtually touching, in other words, when they get to collide with each other, and they just about touch, and they are so close together that we would say that they are touching, there's another force that locks them together. You can almost think of the nuclei as coated with a nuclear superglue or a nuclear Velcro that only works when they're so close together that they're just about touching. This very sticky nuclear force is called the strong force, or by old folks like me, we call it the strong nuclear force, which I think is more descriptive. Okay, so when nuclei overcome this electrical repulsion, they lock together because of the very sticky strong nuclear force. This force only acts if you get them close enough to just about touch. And once they do, they bind together. And the electrical force is still trying to push them apart, but it's not succeeding anymore. Okay? And so what happens is if enough protons bump into each other, you end up making heavier nuclei. And in fact, you're basically doing alchemy. You're turning hydrogen into helium in the core of the stars. So heavier building blocks are built, but those heavier building blocks, heavier nuclei, even though they are heavier, they have less mass than their initial building blocks. In other words, you put two protons together, you end up with something called a deuterium nucleus, a nuclei of hydrogen that has a neutron in it. A deuterium nucleus is slightly less massive than the two protons that started out. Okay? And that's very important. Now, in stars like our Sun, what ends up happening is four protons, four hydrogen nuclei, slam together in several steps to produce a helium nucleus. Okay? A helium nucleus has two protons and two neutrons. In case you've forgotten, a neutron is very similar to a proton, except it has no electrical charge. Okay? It's a similar mass, but with no electrical charge at all. Plus, several gamma rays of energy are released in this process. Okay? So, if you had a chemical equation, or a nuclear equation that would show this, four hydrogens, proton is a hydrogen nucleus, come together in a very complicated series of steps, which I'll show you in the next page, to make a helium nucleus, a nucleus of helium-4, which is made of two protons and two neutrons, plus energy. Now, you might ask, why does energy come out in this reaction? Well, it turns out that the mass of the helium is slightly less, only 0.7%, than the original four protons. So if you put the four protons on one side of a teeny tiny scale and put the helium nucleus on the other side of that teeny tiny scale, the protons would be heavier. The protons would push the scale downward. Okay? The missing mass is converted directly into energy. Okay, so that little tiny bit of mass that gets lost when you turn the four protons into the helium nucleus is converted directly to energy. And not just a little bit of energy, but a lot of energy. The equation that ends up being the answer to this conversion problem is the most famous one in all of modern physics. It's Einstein's equation for the equivalence of mass and energy. E equals mc squared. Okay? It's the equation that many people love to quote. Very few people understand exactly what it means. Well, we're going to understand exactly what it means here. Energy is equal to mass times the speed of light squared. C is the number that is equivalent to the speed of light. That's a little misleading, though. We're not talking about the mass traveling at the speed of light, even though it produces photons that do travel at the speed of light. It's somewhat mysterious how the speed of light comes in here. The point is, right now, what it is, we just think of it as a conversion factor. Mass and energy are two forms of the same thing. And the factor that tells you how much energy is locked up in the mass is the speed of light squared. Now, as you might know, the speed of light is a big number. The speed of light is the fastest speed there is. And if you multiply that big number by itself, you're going to get a humongous number. Something like 6 times 10 to the 19th. What is it? Yeah, that's right. That, 6 times 10 to 16th. 9 times 10 to the 16th. Okay, that's 9 times 10 to the 16th. Sorry, my mental math isn't working right now. The point is, it's a really, really huge number. So what does it mean? It means that mass and energy are two forms of the same thing. Okay, there is no conservation of mass by itself. Mass and energy can be intertwined. They can turn one into the next. Matter can be thought of as sort of locked up energy. Energy locked up in a solid or material state. And the c² tells you that a little bit of mass yields a lot of energy. Let me give you a couple of pretty impressive examples. If you took a paperclip and you took the mass of a paperclip and you could somehow turn the mass of this paperclip directly into energy, you took the mass of this paperclip and multiplied by c², you would get the energy of a space shuttle launch. Okay, now you've probably seen at least video of space shuttle launches. It was a very, very large space vehicle. It takes a lot of energy to launch that thing into orbit. Okay, how about marshmallows? If you took a marshmallow and turned its mass directly into energy, you would get a nuclear explosion. Okay, about the explosion of a typical hydrogen bomb. So, that is nuclear fusion. Now, there are a couple of different types of nuclear fusion inside stars. The dominant reaction within a main sequence star depends on its core temperature, and that depends on the star's mass. In stars that are less massive than about the mass of the sun, or slightly higher, less than about 1.1 times the mass of the sun, we have something called the proton-proton chain as the main reaction. The proton-proton chain goes like this, and you do not have to memorize this fairly complicated chart. What it says is two protons come together, they stick, and one of those protons turns into a neutron by ejecting a positively charged electron. It's called a positron. That connects with another electron, a negatively charged electron, to make a gamma ray. They annihilate, they disappear, and turn into pure energy. The mass of the electron and the positron together is equal to the energy of this gamma ray. Off goes something called a neutrino also. We'll talk about that later. That deuterium is then banged into by a proton, another free proton, and then you get a helium-3. Helium-3 is a little less massive than these altogether, and because of that, that mass is turned into energy, pure energy, and another gamma ray is produced. Okay? This helium-3 finds another helium-3 that was produced in a similar reaction to this. They slam together, out pop two protons, and a helium-4, plus a gamma ray of energy. So if you add it all up, the net reaction is the simple one I told you in the beginning. 1, 2, 3, 4 protons come together in a series of steps. Actually, it's 1, 2, 3, 4, 5, 6 protons, because this happens twice, come together to give you a helium-4 plus 2 protons. So you take away these two from the 6 that you started out with, and the net reaction is that 4 of these protons turn into a helium-4 plus several gamma rays of energy. Okay. A more complicated reaction happens in more massive main sequence stars. This is called the carbon-nitrogen-oxygen cycle, or CNO cycle. Again, you don't really have to know this whole thing, but a hydrogen slams into a carbon, which turns into a nitrogen-13, that decays into a positron and a gamma ray, and a neutrino, makes a carbon-13, gets slammed into by another proton, which makes a nitrogen-14, slammed into by another proton, which makes an oxygen-15. That decays into a nitrogen-15, then slammed into by another proton to make a helium-4. The net reaction is exactly what we had before. 1, 2, 3, 4 protons come together to make a helium-4 plus a whole bunch of energy. Okay, we will continue with this on the next mini lecture.